All right. Good afternoon and good morning, everybody. Today we're gonna have the key switcher seminar hosted by Abhay Ashtekar, who truly doesn't need any introduction. Just to remind you, the format of the seminars, we're gonna have a presentation followed by ample time to discuss. If you have a question, a clarifying question, please do ask it. Otherwise, let's wait for the moment of discussion. Abhay is going to stop in certain places in the talk to allow you to ask also some more in-depth questions. And that's it. I pass the microphone to Abhay.
Okay, so thank you very much. It's a pleasure to be in this seminar. I mean, I think this is a great service, and this whole quiz initiative by Christodoulou and Rovelli and other people has really been extremely stimulating and great for the community. So today, the title of my talk is really The Many Faces of Photons. And this work was motivated in part by the ongoing discussion on testing the quantum nature of the gravitational field through entanglement. But it's of interest in its own right as well, from the fundamental theory considerations as well as experimental considerations. What I'm going to focus on is really the quantum nature of Coulombic interaction. And for technical simplicity, I will consider the electromagnetic fields rather than the gravitational field. And therefore, the Coulomb aspects actually in this electromagnetic case force us to go beyond the standard Fock photons. And that is what I would like to sort of explain in this talk. The considerations I'm saying, just putting forward here, actually go through for linearized gravity in a completely straight, not technically much more complicated, conceptually very similar way. And you can see those things in this paper, which appeared already 5 years ago. Sorry. With Beatriz Bonga, that was written up here. And the details you can see there. And also in this particular talk, I'm not going to be worrying about factors of square root of 2 pi, etc., because that just clutter the slides, and the correct conventions you can also see, or correct numerical factors you can also see in that paper. I'm also going to be use some work that Beatrice and Eric Poisson and Frank Yang did some time later. And there is another kind of there on the web page. If you just say my name and then lectures on gravitational waves, summer school, this was in China in 2021. The first part has to do with photons, and the second part with gravitons. In fact, much of what I'm going to say, not everything, but much of what I'm going to say actually goes through even for full nonlinear general relativity, and you can see that over there. And this is based on early part on discussions with Adrian Del Rio and Miguel Campiglia. And in the last month or two, I've been talking a lot with Ivan Aguio and Eugenio Bianchi. So the organization of this talk is going to be in 3 parts. The first is going to be really a review of standard Fock representation, but then it is using the notions of null infinity, which are going to play a rather important role in understanding the quantum nature of the Coulombic interactions. The second part of the talk, so this is all just free photons, the standard, textbook kind of treatment up here. Then we're going to look at photons created by external sources. This is also something quite well known, but I would like to review it for you. And first I'm going to, because the conceptual issues that are always a little bit confusing. And then first I would like to just take the simple case, namely the sources or source currents, external ones, which are of compact support in space-time. So for example, you shine a laser light and then you switch it off again. It's compact support in space and compact support in time. Another nice example is just sunrise, right? Sun rises in the morning and sets in the evening. And so there is a source there, which you can take to be external classical source, and the photons are coming in and so on. So how do you describe them? That is what we're talking about here. And then the next thing is really more important, which is really when the sources do not have support, which is compact in time. So for example, if you have charge sources, then conservation of charge says that you cannot switch them off and switch them on. I mean, because the charge is conserved, and therefore the source has to be there forever if there is charge up here. And here is an external source, and therefore I'm not looking at interaction between fields and so on and so forth. And then the third part is an interesting part. It is a continuation of the second part up here. Namely, the question is then, what we'll find up here is that the standard notion of photons is inadequate. We need this photons have many faces, and we need another face of these photons up here. And so it's not the, and now what we'll find is that if we look at the radiated angular momentum, it is not really fully captured by the Fock photons. And then one can have experimental demonstration of that the physical photons actually do carry Coulombic information if they're emitted by these external sources. And I already said about that. In the discussion period, I will also be happy to talk about going beyond this. This is a little bit restricted, but we don't have enough time. It is restricted because I'm always talking about external sources, whereas one might want to just look at fully interacting systems between, say, charged scalar fields or Dirac fields and the Maxwell field. Their situation is a little more complicated. One has to resort to perturbation theory. And if there is interest, I can say what the differences are, what the similarities are. Okay. And at the end of each topic, I'll stop. And if you can ask me more questions. So this is just the standard Fock representation. So hopefully I can be quick here. So you look at just source-free solutions to Maxwell's equation in classical theory. And one of the equations says that the field tensor F is exact, and therefore it has a vector potential. So we always might as well introduce a vector potential. And then the second equation, which says that the divergence of the field strength is given by the current. The current is actually 0 here, and therefore we just get this equation up here. And in the Lorentz gauge, then this implies that we only have the wave equation, as everybody knows, but there is still restricted freedom left. I can just add to a gradient of a function, which also satisfies the wave equation. And this restricted freedom is generally removed, for example, by going to Coulomb gauge. In this talk, I'm using the Penrose's abstract index notation up here. And so when I just write A, it's a 4 form. And when I write A with an arrow on it, it is really restricted to a 3-dimensional manifold. So it's a 3 form. And now the configuration degrees of freedom are then in this A. There are 2 of them because first of all, it's a spatial one. And secondly, it is divergence free. So that takes away the longitudinal part and we are just left with the transverse part. And if we use all the Maxwell's equation, then the 4-dimensional A has a property that in fact, this U, the scalar potential is equal to 0. And the longitudinal part is equal to 0, and therefore we're just left with this transferred part. So we do have these 2 configuration degrees of freedom, but they are non-local in space-time. Now, as everybody knows, we can just decompose this vector potential into creation and annihilation operators. The negative frequency part corresponds to the creation operator, and the positive frequency part to the annihilation operator. This really is an operator value distribution, so one has to really smear it with respect to test functions. And this creation and annihilation parts satisfy in the momentum space that transverse to the momentum vector K. The momentum vector K up here. And therefore they only have 2 components. And these are the degrees of freedom of the photon field up here. So this, like, if you like, this index A represents the polarization degrees of freedom. This index B, sorry, represents the polarization degrees of freedom. And then what about one photon state? So of course, generally one just considers the A hat of K dagger and operates on vacuum, and then says that I got one photon state with the momentum K. But this is, of course, not normalizable. In any case, it's just a basis. But what is the total Hilbert space? So to get the total Hilbert space, we have to smear this with respect to a vector field up here. And I get I get a one photon state. A general one photon state will be obtained by smearing it with respect to D3K up here. And then the scalar product is given by if I give an F and G to such one photon state. So F and G are two photon state. Then if I take the inner product there, that is just given by D3K times G bar times G. And I'm putting in H bar factors explicitly everywhere just to sort of say that this really is a genuinely quantum mechanical notion. H bar goes to 0, this doesn't make any sense. And my conventions are the textbook conventions in which creation and annihilation operators have delta distribution normalization. Now, if I look at this object, which I call F up here, a B of K. So given such an object, it actually determines a classical solution because I can just put it in here and do the same kind of decomposition as I did.
Can I just ask a quick question, clarifying question? Yeah. In this expression for this ket of FB, on the left-hand side, you have F of BK times A dagger BK. So is there any sum over these polarization states on the left-hand side, or is it just 1B?
This is summed out. This is the standard summation notation.
This is a sum. So then on the right-hand side, you still have the B index on the F, right?
Right.
Could that be there?
Yeah. So that because I'm allowing arbitrary polarization.
I mean, if you're summing over the polarizations on the left, then the right-hand side should not depend on the polarization, right?
So okay, that's fine. Okay, you're right. So there should not be indexed. You're right. Thank you.
Oh, okay, thanks.
Sure. Thank you. Yeah. So now, so I got here. Yeah. So I correctly dropped it here. It should not have been here either. Good. So then the statement up here is that we got this given any smearing function like that, I got I can also construct do the same transform and get a field in the physical space-time. And then this will be the positive frequency part, and this will be the negative frequency part of that particular field. And because I got this e to the ik dot ed, it follows immediately that in fact this is this FB is going to satisfy the wave equation and then the Coulomb gauge condition. And then because of the Coulomb gauge condition, and since this is only 3 dimensions, so it has no 4th component, we also have the Lorentz gauge condition. Okay, so if I look at the one photon Hilbert space, what is it then? Either I can say that these FB of Ks, or I can say that it is really the solutions up here, which are just solutions, homogeneous solutions to the Maxwell's equation in space-time. There's a momentum space description. Here is the space-time description. And then, so one photon Hilbert space consists of positive frequency solutions because I'm of source-free Maxwell's equation. Now you can construct a coherent state, and that coherent state, which is peaked at the classical solution AB, is just given by exponential of the creation operator times AB smeared with AB up here, operating on the vacuum. And so there we got this nice intertwining between the classical theory and quantum theory. Now, this is all very well known, but often is not sort of brought to forefront in most textbooks, textbook presentations. And so I want to emphasize that there are kind of nice intertwining between classical theory and quantum theory. Namely, on the one hand, a positive frequency classical solution represents an element of the Hilbert space, one photon state. But of course, I can just superpose those one photon states and get a coherent state. So the classical solution corresponds both to a coherent state and also a one photon state. Now, the awkwardness of this description is that you need a 3+1 decomposition into space and time. There is a non-locality because we're decomposing this into Lorentz and into longitudinal and the transverse part up here. But I want to emphasize that this is just kind of a in-between tool. All the physical results, in particular the inner product that I wrote down up here, that inner product is completely Lorentz invariant. And in presence of sources, there is some confusion because what happens is in the literature, because what happens is that in presence of sources, we cannot really use this description. We cannot have both the Lorentz gauge condition and dA of A equal to 0, because as I said, that immediately implies that A naught itself is equal to 0. The scalar potential is equal to 0, but in presence of sources, it is not equal to 0, and therefore you need more care. And the nice thing is that if you go to null infinity, then all these problems, these awkwardnesses disappear, and you have got a nicer description, which then is going to be extremely helpful in our understanding of what happens in presence of sources as well. So this is the part which is probably less familiar to some of you, and therefore let me be a little bit more detailed. So what we're going to do is we're given a Minkowski space, and we're going to complete it by adding it a boundary. And that boundary is called script I or scry, and it's called null infinity up here. So the idea here is the following, that the radiation travels in null direction. So if I have a radiation, if I light a point source here, then the light will travel in null direction always. It will travel in null direction like that. And so you can, just Einstein used to say, we can just take the ride with the light front and basically arrive as far as you can go in the limiting case, if you like, the resting place of this light ray up here. And that is a limiting point, and we add all these limiting points, and that is a null boundary scry. And that you can do it in the future with future directed light cones, and then you get a null surface, which is called scry plus, or I can go in the past directed light cones, and I will get a null surface, which is called scry minus. These whole details are not essential, but just to get the basic ideas in mind, what are we doing up here? Well, we can start with the Minkowski metric, just minus dt squared plus dr squared plus r squared d omega squared, and just use this retarded time u, which is equal to t minus r is equal to u. So this is u equal to 0. This is a null cone. This is u equal to u1, u equal to u2, etc., etc. So then I just substitute, and I get the metric of this form. Just substitute for dt. I get minus du squared plus minus du 2 du dr plus r squared d omega squared. So this is just a spherical line element, and this is the metric in the RT plane. And now we want to go to r equal to infinity. We want to go to the limiting point up here. So we choose, r is therefore not a good coordinate on the boundary because it is infinite. So we choose a conformal factor omega, which is 1 upon r, and multiply the metric by this conformal factor. And then immediately the metric becomes omega squared du squared. This term just changes sign because of 1 upon r and becomes twice du omega. And then this term up here, r squared disappears and becomes du omega squared. And the interesting thing is that this metric now is perfectly well defined at omega equal to 0. At omega equal to 0, this term disappears, but this is a non-degenerate metric with signature minus plus plus plus, just as the Minkowski metric was. So we got here hatched metric, and therefore this is called the conformal completion. The hatched metric is conformally directed, and it's conformal completion. So we're going to null infinity along this null rays up here, u equal to constant. Now topologically, this omega equal to 0 surface is coordinatized by u, theta, and phi, because omega is equal to 0 there, r is equal to infinity, or omega is equal to 0. Therefore, we got these 3 coordinates. So theta phi is a 2 sphere, and u is runs on the real line, and therefore it has a topology of S2 cross r. So sometimes it is convenient to just think of it as a cylinder. This is the cylinder. This cross section here will be S2, and this will be R. And then we can introduce a null tetrad, which is called the Newman-Penrose tetrad. All that this is not absolutely essential. We can just do it with tensor fields, but literature is full of these things, and therefore I thought that I should just introduce this notation once. So what this null tetrad is the following. First, we can choose the null vector, which is tangential to these light rays which are going out, and that null vector is called L. And then scry itself is a null surface. Therefore, its null normal is also tangential to it. So we got this null normal up here, and that is called N. So I got L and N are 2 null vectors. If you like, these are the null vectors in the RT plane. Here are the detailed relations, if you like. And then I also have a 2 sphere, And on the two sphere, I got d by d theta and d by d phi. You just take a linear combination of d by d theta and d by d phi like that with a complex one. And the interesting thing is that that complex combination is called M. And therefore, I got L, N, and then M, and since it's complex, also M bar. And these are four independent vector fields. They span a null basis. All of them are null. So the scalar product of M with M is 0, that of L with L is 0, and N is equal to 0. The only non-trivial scalar products in this null tetrad are L dot N is equal to -1 and M dot M bar is equal to 1. So these are not important. What you just have to remember is that you've got a null vector which is going like that is N, and L is a null vector like that, and M bar are like that. So if you restrict yourself to scry, then you have got null vector N, and you have got vectors here M and M bar. Now, Maxwell's equations are conformally invariant, so we can just take the field tensor, and that has a well-defined limit on scry. And what I can do is to just look at this field tensor and plug it into it with these vector fields N and M, N and M up here. And it turns out that this component of the field always falls like a 1 upon R, and therefore the coefficient is called phi 2 naught. Since this is falls as 1 upon R, phi 2 naught is called the radiation field because it falls like 1 upon R. If I take the combination Ln and M bar, that is called phi 1. Its leading coefficient leading term falls like 1 upon R squared. So this captures the Coulombic degree of freedom, the Coulombic information. And then if I take L and M, I get phi naught. It also has interpretation, but that's not going to be relevant for us. So I'll just going to focus on these two quantities at the moment. Maxwell tensor has 6 real components. This is too complex, and therefore we got here. So I got 3 complex scalars which capture the 6 components of FAB. So the physical content of this is the following. As I already said, this phi 2 naught is called the radiation field because it falls like 1 upon R. And if you are, for example, if I got a Maxwell field and you want to know how much energy was carried away by this Maxwell field across scry up here, then that is just given by just integral on that little patch of scry. You want to know how much energy went through a little patch of scry times phi 2 naught squared. Alternatively, what you can do is, you see phi 2 is just obtained by taking FAB times NB and then M up here. So I can just construct a one form at EA. This one form is transverse to N and E in N equal to 0, just by definition, because if I plug another N, I will get 0. And therefore, it only has 2 components, and these are the 2 radiative modes. And then this what I call here phi 2, as you can see up here, phi 2 is just given by EA times MA. These 2 components are just these up here. Now phi 1.
Excuse me, like I think Marius has a question.
Yeah.
It is. Marius, you want to unmute yourself?
Hi, sorry, can you hear me? It was a small clarifying question. I was going to do it later. I just wanted to ask about how important is spherical symmetry for this formalism, or is it just topological?
No, there's no spherical symmetry issue. This is just the Minkowski space. So I'm using, if you like, the Minkowski space. So sources and so on don't have spherical symmetric.
Okay, so the sphere before it's not the spherical symmetric geometry that you're talking about.
It's just a 2-sphere Minkowski space. I'm just using radial coordinates, the radial coordinates, r theta phi t coordinates.
Okay.
It's not x, y, z, t coordinates. There's no spherical symmetry. Nothing is physically spherically symmetric.
All right.
Yeah. So this is just completely general description of completely general Maxwell fields. Okay. So the Coulombic information is just captured here, and then this phi, if I take this phi 1, Coulomb, and if I integrate it over to sphere, I think I lost a factor of 2 pi, but let me not worry about it. If I integrate on a two sphere, I just get the real part will be the electric charge, and then imaginary part will be magnetic charge. But of course, by our assumption, magnetic charge is 0 because we assume that FAB equal to grad AB. And so the source-free solutions, if the solution happens to be source-free, as we're considering, not only is the charge zero, but because the source-free solution has no sources, so electric and magnetic charges also vanish. But in fact, the whole Q, so the total charge is equal to zero. Now, there's also an equation of motion which comes from Maxwell theory, which says that the time derivative, this is just on screen now, the time derivative of this phi1, the Coulombic part, is just given by the Earth is an angular derivative, theta phi direction derivative of phi2 naught. And therefore, I can just integrate it, and I write this as phi1 naught to be equal to minus infinity to u of Earth of phi2 plus an integration constant. And that integration constant is identically zero if you have got source-free solution. So this it's not a constant, it's a function of theta and phi. It's constant in u, constant in time, but okay. And what this says is that in fact, phi1 has no new information, because if you know phi2, I can just get phi1 for source-free fields. For source-free fields, then all the information at scry is contained in this electric field, if you like, FAB and B, or in this field phi2 naught. Okay. So these are the two components, the two radiative modes, as you would expect, that all the information is in these two radiative modes. So you can extract the full solution from there. And therefore, this phi2 naught or E, if you like, they're completely equivalent. That is the initial data. You can specify it on scry plus, and that will give you determines the solution completely. Now, what about potential? Well, the potential again has a property that it is also transverse, and therefore it has a limiting behavior, and that limiting behavior. Yeah. So that limiting maybe I'm not writing the zero on the A I think notation. So this A is just is the potential at scry, and then I can just take its MA component, and that just gives me A2 naught. This is exactly what had happened with respect to the field strength. In the field strength also, we just had taken we had this EA, and I just took its M components. I got this EA up here, and I just took its M component to get phi2 naught. So we do the same thing with A. I get here A2 naught up here. And then the relation is that the time derivative of A2 naught is equal to phi2, and the angular derivative of A2 naught is equal to phi naught. But in general, there will be constant of integration, but this constant of integration is equal to zero. If you have sources presence, then this Q is not equal to zero. And as we'll see, that has very interesting ramifications. But for the source-free solutions, for ordinary photons, Q equal to zero. So again, just like all the information is contained in these radiation fields, it's also contained in its derivative, in its potential, because the time derivative of this potential is equal to the radiation field. This is completely general source-free solutions of Maxwell theory, and this is a classical theory. What about quantum theory at scry? Well, for quantum theory at scry, we can also define a vector operator corresponding to the vector potential, can decompose it into the negative and positive frequency part. The negative frequency parts are the annihilation operators. Again, this index B up here, the index B up here refers to the two polarization degrees, and I'm taking the Fourier transform only in frequency space. Theta and phi could have taken the YLM decomposition, but I'm not doing it, and therefore this object depends on omega, theta, and phi. In the Minkowski space, that depended on A of k. Again, three objects, k1, k2, k3, if you like, and now it depends on omega, theta, phi. Again, this is transverse. It is perpendicular to it, so it only has two components, which are given by A2 naught, as we saw before up here. And we got this convention of the creation annihilation operator. Now, what about one photon Fock space? Well, if you give me a one form F, I can take its Fourier transform. This is the Fourier transform of this. And then the one particle naught is just given by d omega by omega times d2s. So it's like integration in Minkowski space. We had three-dimensional integration of momentum space. Now we got one momentum and two space times this up here. Now, classically, if you are given a null datum, if you are given me this thing of it, then, and if that null datum, classically this, if you give me this field, as I said before, you get a unique solution of Maxwell's equation in space-time. Now, classically, if you give me a null datum, which is say smooth on scry and falls off in U, say in short space, then it's a perfectly fine Maxwell field that you will get inside in this interior. But if in fact, because of this omega up here, if f tilde at 0 is not equal to 0, then you got logarithmic divergence and the norm diverges. So perfectly reasonable Maxwell fields from the classical point of view can have infinite norm, and therefore they would not define a one photon Hilbert space. They will not belong to the one photon Hilbert space. And this, when this happens, what we have is we got these infrared sectors. These A's are not elements of the standard Fock representation, but they are elements of some other dressed Fock representation or infrared Fock representation. And therefore, they're not the standard photons. They carry some additional information in them. And these are very important for scattering problems. But for this talk, I'm not going to go into that because there's another complication which is not relevant. But I want to tell you right here that even for free field theory, there's another phase of photons which are caused by infrared sectors. So summary of null infinity, we can isolate the 2 degrees of freedom locally. They can be thought of as living in this one form EA, which is just given by EA one form. It's just equal to FAB, the Maxwell tensor, multiplied by null normal to scry. Or you can think of it as a pullback of the potential, or the same information is contained in A2. So this is a complex scalar, and this is a vector with only 2 components, and the same thing here. The Coulombic information is contained in another two real functions or one complex function.
Question?
And that is just given by the angular, that is just given by the angular derivative here. So the radiative part is given by this is phi1 naught up here is just given by du of A2 naught, whereas phi1 naught is given by this. Go ahead, Weston.
This is Carla. A question about the end of the previous slides. There's this recent work by Bob Wald and Gautam Satish Chandra, and in which they argue that Fock space is, Fock space is, Hilbert space is not sufficient. They want to go to a algebraic description. Is that to address the infrared sector that you just mentioned at the end of the last slide? Is the same thing that they're discussing?
So these infrared sectors is something that I pointed out in the 80s, I think, and then the Hilbert spaces and such thing are constructed. And now I think there's been a lot of interest in it, primarily due to Andy Stromiger's work, which just came from scattering amplitudes work up here. And Wald and collaborators, his students and collaborators, they are writing this thing, and these are exactly addressing these infrared sectors. And they want to say that, well, to completely understand them in full interacting theory, right? Not in the free field theory, but in the full interacting theory, one has to perhaps go to the algebraic framework. I mean, they don't have any proof of that, but that is their suggestion.
Okay, thanks. Yeah.
Okay. So a scry is null. And so another interesting thing is that there are no constraints here. So, in space-time, the electric field has to satisfy EA, dA equal to 0 or 4 pi, and dA, BA equal to 0, or source up here. And the statement here is that there are no constraints. Even if there are sources which are massive, they don't register on scry, because what happens is that if you have a massive source, that massive source will just go like that. So it will go to I+, it doesn't register on scry. Only massless sources, if you like, if you have a massless field, that will go to infinity up here. So even in presence of massive sources, the statement is that that there are no constraints. And then there is a one photon Hilbert space that we had can be constructed very naturally. Namely, you just start with one forms FB on scry satisfying FB and B equal to 0. So this is just a one form on scry up here. And then the norm is just given by d omega by omega times this, and the necessity And then the statement is that this makes it very clear what the infrared sectors are. This is how I found that it's very nice intertwining between infrared sectors and SCRI, because it brings out the meaning why these sectors arise very, very clearly. That this given any smooth configuration like that, it is perfectly fine as a classical field, but it does not define a one particle Hilbert space element of the one particle state unless this vanishes at omega is equal to 0. And then the scalar product on the scalar product of this Hilbert space up here is in fact Poincare invariant, but in fact it is even a BMS invariant. And in answer to Carlos' question that was asked a few minutes ago, if I were to go to gravity, then again we got these infrared sectors, and very interestingly, that those infrared sectors have to do with the extension of the Poincare group to the BMS group up here. Okay, so this is a part one, and this is kind of an introduction. Are there any further questions? Okay, so let me now talk about the photons emitted by classical solutions up here. So this is a part two. So what we're looking at now is the external current problem. So there is an external current. So, and this is a classical current, therefore it is just multiplied by identity. And I'm looking at photons that are created by this classical current. Let me consider the simple case first, when the source is of compact support, as I said, like a laser beam or like the sun, which rises in the morning and sets in the evening. It's a compact support in space-time, say. I mean, we can just model it as a source of compact support in space-time. And now in presence of sources, now we cannot use both Lorentz and Coulomb gauge because they can be, it just is not consistent with the presence of sources. And then the statement is that, however, this is in the books, but not fully well known, that however, we can use just the Coulomb gauge. Of course, this violates explicit Lorentz invariance, manifest Lorentz invariant. Everything is Lorentz invariant, but this will violate the Lorentz invariance, manifest Lorentz invariance. And so we can go to the Coulomb gauge in which dAA equal to 0, and you can just impose boundary conditions. And even without imposing the Lorentz gauge, in fact, these conditions automatically fix the gauge completely. And this is even true in the source-free case. So if you like, yeah, let me not go into it. In the source-free case, this plus boundary conditions also say that you are in the Lorentz gauge. But in the case with sources, we cannot have both. So this is a side remark. Now, classically, we got a retarded solutions. And the retarded solution satisfies source-free equations in the future. So what I have is, I have drawn this picture of space-time. I try to be realistic. Our past is all nice and green, and our future is rather gray with all the pollution and everything. So these are just a slight side joke up here. So I got here space-time, and so I got here SCRI. SCRI plus is here, SCRI minus is here, and this is my source current. And this source current emits photons, and they go out to SCRI plus up here ultimately. Okay. So classically, what happens is the following. We got some retarded solution produced by the sources. So if I have zero solution here, then in this region, I will not have zero solution, but I would have the retarded solution. And this retarded solution, so I've drawn here a Cauchy surface to the future of which there is no source, and another source Cauchy surface to the past of which there is no source. So sigma 1 past is the past of sigma 1. In this sigma 1 past, I got source-free solution, and sigma 2 future, also I got source-free solutions up here. So if I look at, so classically, we got the retarded solution, I just mentioning up here, and that vanishes in the past up here. And then in the future region, therefore I can just, it has the form that the retarded solution is exactly as before. It's a source-free solution, so it has some F, and then positive negative frequency decomposition. Now, any solution to the inhomogeneous equation, so here I looked at the solution which has vanished here, but if I take any solution of the inhomogeneous equation, and supposing it agrees with some solution which is in green, AB in green in the past up here, so this is a solution of the homogeneous equation. Since this is a solution of the homogeneous equation, I can extend it to all of space-time as a solution to the homogeneous equation. And again, I got a solution to the homogeneous equation, which is the gray up here. So the future solution is equal to the past solution plus the retarded solution. So this is something that is obvious. That's what is happening up here. And therefore, the evolution from this region to this region corresponds to displacing the past solution, adding to the past solution, retarded solution. So it's called displacement of the solution via the retarded solution up here. Now, in quantum theory, I mean, I'm just telling the final result. The same thing is true. I got, in the distant past, I got this green operator value distribution. And in the future, I got this, in the distant past, I got the green operator value distribution. In the distant future, I got the gray operator value distribution. And the future A is given by the past A operator value distribution plus a multiple of identity, which is just the source, is just the retarded solution. And now, so these two objects are just as we saw before for homogeneous solution to Maxwell's equation. We can just do this creation and annihilation operators. But these creation and annihilation operators are the gray ones are different from the green ones up here. Namely, the gray ones are related to the green ones just by the negative frequency part of the solution of the retarded solution, which is just FB up here. So just because the solution itself in the future gets an addition of retarded part, the annihilation part gets an addition of the negative frequency part of the retarded solution up here. So that is the upshot of the evolution up here. And therefore, it follows immediately that if I take the past vacuum, but I operate it by the future annihilation operator, then the past annihilation operator will annihilate it, but I am just left with FB. So therefore, the statement is that the past vacuum is an eigenstate of the future annihilation operator with this eigenvalue. And now everybody knows that as soon as I got such eigenstate, it's a coherent state. So the past vacuum with respect to future is a coherent state, and the coherent state is peaked at the classical solution. So this is what I was telling you before, that we got this nice relation. Classically, we would say the source produces for me a retarded field, and quantum mechanically, we say that source starting with a vacuum, and classically it produces for me this retarded field, and then starting with a quantum vacuum in the past, in the future, it produces for me the coherent state, which is peaked at that classical solution. In the Schrodinger picture, just one second, let me finish this. And then in the Schrodinger picture, the vacuum in the past region evolves to the coherent state in the future region. And there's a well-defined unitary evolution in the Fock space. And the proviso is always that the one particle norm is finite. That is to say, that will be the case if there is no infrared problem. So I'm assuming that source is such that there are no infrared problems, then the future, the past vacuum is a normalized state and it's a coherent state in the future. Question, please.
It seems surprising that wherever the source is, you always end up in a coherent state, not any other more complicated state. Is there a simple way of understanding that?
It is just this, right? The creation and annihilation operator. It doesn't really care about anything else. I mean, if that had not happened, it would be terrible, right? Because, for example, you got radio started working even before quantum mechanics was invented, right? And so they had this dipole moment, which is they started in the morning, dipole moment was oscillating, and they switched it off in the afternoon. And then I got this transmission up here, the transmission went on. And we could calculate, we could receive our receptor, right, radio, just using classical Maxwell theory. And then quantum theory comes. And now you say that here is some source up here, and it's actually emitting these objects up here. And then the quantum answer will be very different from the classical answer. Why did radio work? Well, it worked because the quantum answer is really mimics the classical answer in the external potential problem of compact support, and we just get the coherent state. And the simple answer is, the simple relation is just this, right? And there's nothing more. We can talk about it after the discussion.
Yes, right.
Yeah. Okay. And again, the structure I said up here, I talked in the green region and the flat region up here. If the source were actually going all the way from I minus to I plus. Then, of course, this green region will shrink to Scri minus, and the gray region will shrink to Scri plus. And therefore, the structure is clearer in this Scri plus. Namely, what would happen is that if you give me a vacuum state up here, it actually evolves into coherent state on the future. So I'm saying that that's a consequence of what we talked about if the source of compact support, but it's also going to be true if the source is of not of compact support in time. And that is what now we are going to talk about. So supposing the source is not of compact support in time. So I got this source up here, which is not a compact support in time up here. And I'm assuming that in the distant past, the source has some regularity. In the distant future, it has some regularity. I don't have time to go into the details of that. Then the statement is that I got a retarded solution of this source up here. And then that retarded solution means that nothing is coming in from Scri minus. And therefore, on Scri minus, I got radiation field is 0. And the quantum theory, I got a vacuum. And what I'm trying to see is what happens at Scri plus. So at Scri plus, what happens is that I got this, classically, I got this field, the radiation field AB, or if you like, phi 2 naught, which is a time derivative of this field up here. And that is transverse, that is perpendicular to N up here. In that sense, it is transverse. Or the same information is, as I was saying before, is captured in A2 naught. I just take its component in this complex basis vector on the 2 sphere. Now, assumption here is, I made an assumption that there are no infrared sector. There's an assumption about on the source up here that the retarded solution is such that the value of A at U equal to minus infinity is the same as the value at A at B equal to plus infinity. If not, I will have to worry about the infrared sectors. And just for the sake of argument, simplicity, I'm just assuming that is not the case. Of course, we can deal with it and there's no problem. Already in that case, we'll have to go out of the photon-Fock space. But here I'm trying to look at another aspect of the photon-Fock space, which has to do with the Coulombic interaction. And so this exhausts, and then this condition up here exhausts the gauge freedom. We can exhaust the gauge freedom by demanding that AB goes to 0 at both ends. What we know, no infrared sector says that the value of AB here is equal to a value of AB equal to 0. But we can make both those values equal to 0. Is basically because A satisfies A dot N is equal to 0. And therefore, the freedom that I got is AA goes to AA plus gradient of F, where NA grad A F equal to 0. So F cannot be time dependent. It only can depend on theta and phi. And I can just choose that dependent on theta and phi to say that at minus infinity, that AB is 0. And then that makes it 0 in the future. Okay, so the two radiative modes are in this electric field or in phi 2 naught, which are just given by the time derivative of this potential up here. And the Coulombic information now is given by, in the previous case, without sources, was just given by A2 itself. But now we have an additional integration constant, right? Because we had this integration constant, which was equal to 0 if there are no sources. But if there are sources, then there is an integration constant up here. And this Q is such that if I take the real part of phi 1 naught, if I integrate, I get minus 2 pi Q. In the previous transparency, I had forgotten, I omitted the factor minus 2 pi. But that is by this equation up here, it follows that is the same as f of A2 plus Q. And the f of A2, because of this angular derivative, it turns out that the two sphere integral is identical to 0, and you get the same as the integral of Q. And therefore, this Q is really determined by sources, by what the sources do at I minus up here. And related to the previous section where I got source of compact support, the point is that what was previously sigma 1 in this case has become Scri minus, and what was sigma 2 has become Scri plus up here. But other than that, it is formally the same. And therefore, in quantum theory, again, as in the previous part, I got the creation and annihilation operator on Scri plus, and the green ones on Scri minus. and green ones on Scri minus. And again, the creation operator on the Scri plus is given by the one on Scri, sorry, the creation operator are related by that formula. And then the statement is that I got the vacuum state, which was on the past, is going to be a coherent state, which is peaked at the retarded solution at the future infinity. So this is exactly the same as before. But the new element is the following, that in this representation, this is the Fock space, but on that I have to represent my field operators. And my field operators are phi 2 naught and phi 1 naught. And there's also phi naught naught, but I'm just ignoring it for the moment. And so what happens to phi 2 naught? Well, phi 2 naught is exactly as before. Phi 2 naught is just given by this operator. It will be just given by the time derivative of A2 naught as before. But the new element is the real part of phi 1 naught is not given by the earth of, this was this, what I call earth of A2 naught, which in the index notation is just the spherically symmetric two-sphere integral, the two-sphere derivative of A. So it's divergence of A. A, you can think of it as living on the two-sphere because it is perpendicular to N, right? Yeah. You can think of this A as living on this two-sphere because AA and A equal to 0. So it only has components along M and M bar up here. And what we're doing up here is just taking the divergence. We're just taking here divergence with this two-dimensional divergence plus this. So without sources, we just had this term, but now we got this new term up here. And as I said, that E just given the time derivative here. So this is not new. The new part is up here. Thus, the operator phi 1 naught is represented differently from the Fock representation. And this corresponds to an automorphism, a mapping on the algebra of observables to themselves, which sends phi 2 to phi 2, there's no, or E to E, if you like. But phi 1 is now sent to real part of phi 1 is now sent to real part of phi 1 plus this extra term up here. In terms of the vector potential, this corresponds to vector potential goes to vector potential plus a C number, one form up here. And that one form has to have the property that is two-dimensional divergence, or I could have also done it with the just like with A2 naught. I could have looked at the M component of this omega, and then F of omega will have to be equal to Q, or two-dimensional derivative divergence of omega is equal to Q. So I have to solve this equation up here. And now we got a mapping from the algebra of observables to themselves. And we ask, is there a unitary transformation on the Hilbert space which makes this manifest? If that happens, the automorphism is inner and it is unitarily implementable. But in this case, it turns out the answer is no. And the answer is no because this Q up here has no U dependence. It is there forever. So if I take the Fourier transform here of U, if you like, it has a pole at omega equal to 0. It has delta distribution at omega equal to 0, the Fourier transform on that. Because of that, this is not the unitarily implementable. And that, if you like, if you do it formally, then the vacuum state on Scri minus would be a coherent state peaked at something like this omega up here, but the Fock norm of this omega actually would diverge, and therefore the statement is that is the reason. The vacuum state of Scri plus would be sent by this would be unitary mapping to a coherent state, but that coherent state really doesn't exist in the Hilbert space because the one particle norm of this diverges. So therefore, there are two complementary descriptions of the photons created by the external current J in this section 2b, where the current is not of compact support in time. First will be to use a standard Fock representation with A and A dagger as before, and then represent E as just du of A and real part of phi 1 as this plus this. So it's a non-standard Fock representation. You see, what is important to realize is that neither the Hilbert space nor the observables constitute the representation. It is a combination of the two that constitute the representation. We can keep the Hilbert space the same, but change the representation of the physical observables, or we can keep the physical representation of the physical observable the same, but change the Hilbert space. And the statement is that in this particular case, no matter how you do it, you get a unitarily inequivalent representation. So one would be to keep the standard Hilbert space, the standard Fock space, but change the form of the operator. The physical observable phi1 which has a Coulombic aspect, is not given by the Fock expression, which will be just that, but has an additional term up here. Or we can use a displaced Fock space where the new vacuum is really peaked at this omega up here, which is not in the Fock space. So it really is a different object altogether. And then use the same expression for the operators as before, with the fact that I got this displaced Fock representation. The outcome is that the one photons created by this particular source that I got here, this source which is not switched off, the photons created by that source are not in the standard Fock representation if Q of this Q is not equal to 0. And what is this Q? Well, this Q is something that you can calculate looking at just the retarded solution from here, and get the solution up here, retarded solution, and see what is real part of phi1 Look at it, what happens to it in the distant past. Is it 0 or not? If it is not 0, this term vanishes in the distant past, and therefore is this 0 or not? Does this vanish or not depends on this Q. So calculate the retarded solution, look at what happens to the Coulombic aspect of it in the distant past, and if it is non-zero, then these photons created by the sources are not going to be in the Fock space. They carry extra information, they carry Coulombic information. And the third part is short, therefore I'll stop for questions, which, just one second. The third part is short, and I'm not going to do it. I just want to tell you that here, in the third part, what I want to show you is that, in fact, these are not just abstract mathematical things, but they have physical consequences, and you can make it explicit as to how the information carried by the Coulombic information carried by these photons manifests itself. Marius.
You have already explained this to us a couple of weeks ago. So my question is a question that I didn't make to you then. If you have any intuition, an intuitive way to understand why we see from your results that we can read the charge information in the rotation flux, but we don't see it, I don't know, in the translation, for instance. What's special about the rotation intuitive that keeps the
That's the third part, which because I'm not explaining it yet.
Okay.
So I would like to,
okay.
So I mean, it's good because this is one of the points that is not going to be on the slide, but I want to explain it. I mean, this is an important point that I would like to explain. Yeah.
Okay.
First, let me state what I had said that Mario was referring to. So the question is here that here we just saw mathematical construction that these photons created by the sources are not in the Fock space, or not in the Fock representation is what I should say. They are not in the Fock representation. So because they carry additional information, which is the Coulombic information, and the Fock photons have no Coulombic information at all. So the question is now, is this Coulombic information anyway manifest? And to me, of course, it's manifest in many, many ways, but to me, a very striking way that it manifests itself is through angular momentum that is radiated away. So we got these photons which are going out to infinity, and they're carrying energy and momentum, and that also carrying angular momentum. And now we want to see what the expressions are of this angular momentum and so on and so forth. So what is the flux at scry? So maybe I should just draw a picture here. That will be easier than going back and forth all the time. So I got here scry, I got some source up here, and I got scry plus, and I got scry minus. And this flux, and this is radiated up here. So what I would like to look at is, really, I like to look at a little patch of scry. So I would just look at a little patch like, it doesn't have to be around even. I could even look at just a little open region of scry here, if you like. But for simplicity, let me just consider a round one. Between two instants of time, for example. I can just consider a patch of scry, and this is what I'm calling delta scry. So the question is how much the radiation is flowing through this region of delta scry. And And what I would like to know is how much energy, angular momentum is carried away. In fact, those of you who know about BMS group, how much BMS momentum is carried away, you can calculate explicitly. But how do we calculate? Well, for the Poincare momentum, that is to say energy, momentum, and angular momentum, and the boost momentum, the flux across Craig is something that we know. We all know from textbook that is always going to be given by across any surface. If you give me any surface up here, and that surface here is delta scribe, that surface is delta scribe up here. The flux across the surface is always going to be given by the renormalized T hat AB in Minkowski space, just corresponds to normal ordering times whatever the symmetry vector field you have got. So if it is energy, it is time translation, momentum, space translation, angular momentum, rotations, and so on, times the normal to scribe, and then du d2s. And so this is the symmetry vector field, and the flux corresponding to that symmetry vector field is just going to be given by that. Now you just take the expression for this, and that expression for TAB, as you know, is just given by FAC FCB minus 1/4. Or maybe I should write it better. Another way to write it, the same expression is just going to be FAB, FAC, FCB plus star FAB. This is the same expression as usual, but the usual one, but written slightly differently. And that is what the stress energy tensor is. So this is the stress energy tensor. And so what I can do is take that stress energy tensor and expand it out as we did in the very beginning. The information in F, as I said, is completely contained in these three scalars. So you can just expand it out explicitly and see what you get. And again, this is all in the, you can find the details in this paper with Beatriz Bonga that I referred to earlier on. And what we find is that for the energy radiated, this is just given by, so this I'm breaking Lorentz, manifest Lorentz symmetry. I'm choosing a rest frame, and I'm just adapting my conformal completion to that rest frame. So then the statement is that in that case, the time translation just becomes d by dn, or d by du, or if it's time translation, it's just n itself. And you find in that case, it's just normal order of phi2 naught square, the radiation field square. Or I can also write as normal order of this, what I called previously E hat A, E hat A, E hat B, normal order of that instead of phi2 naught square. If I take, say, for example, a z component of the momentum rate that is carried away here, I will get integral delta square of phi2 naught times, I get here, instead of the time translation corresponding to function 1, space translation will be in the z direction will be cos theta, in the x direction will be sine theta cos phi, and in the y direction will be sine theta sine phi. So I'll just get this quantity. And this only depends on the radiation field. So in our representation, the non-standard, non-Fock representation that we got here, the radiation field is represented exactly as in the Fock representation. So there is no change in the energy radiated away or in the momentum radiated away. But if I look at the angular momentum radiated away, and this was Marius's question, I will just state it first, explain everything, and then answer his question. So if I look at the angular momentum radiated away, then I get this to be equal to imaginary part of phi2 naught times phi1 naught. And again, normal order, and then sine theta. So in this case, this is the question that Marius was asking. It is not just given by phi2, or even phi1 already phi1 appears up here. And imagine that, remember that phi1 representation, if I were to just use the Hilbert space with the standard Fock representation, then phi1 is represented by the Fock expression. So this will be just the radiative part plus this. Now I got this plus q up here. So the angular momentum that is radiated away knows about this q, knows about what the source was doing at minus infinity, if you like. That is what is determined what this q of theta phi is. So it knows about that. And that distinguishes it. The expression is different if it was a Fock photon or if it was this photon carrying the Coulombic information. So this is the difference between the two, and therefore we could measure angular momentum, and then we could actually see that is it given by this or is it given by this. The energy carried away will be given by that, that is completely determined by phi2 naught, and phi2 naught, remember, is just given by a2 naught time derivative. But and here I got a space derivative of a2 naught. So these are kind of the radiative modes, radiative information up here, but this is not captured in the radiative information. So can we measure it? I'll come back to the question about why here you got only phi2 naught and here you got phi1 naught. I'll come back to that in a second, but let's accept it and just let me do the class transparency, which is what can we do it experimentally now? Can we measure this experimentally? So again, what I'm going to do is to take a very simple example. And this is an example in which I'm considering a rotating charge sphere. So in this case, the source is spherically symmetric. But everything I set up here, up to this part, in particular, the external source problem here, and the result that I was talking about, where you got the real part of phi1 naught is represented by this expression. That does not require spherical symmetry of the sources. But this is something that you could do in the lab. And people at Vienna, in fact, have all these beautiful small sources, very, very good small spheres, extremely small spheres. So we could do this experiment in lab. So what you do is you take this little sphere, and that little sphere is not doing anything in the distant past. It just sitting here. And then you start spinning it. So you slowly spin it up, spin it up. Here there's maximum spin. And then you let it spin down again. So here it is being spin up, and then it's being spun down. And now I'm just looking at some little region up here of delta scri, and oops. I'm looking at some little region here of delta scri as before. Again, as I said before, I could also look at just little patch of delta of scri up here, and a delta scri could be that. So you look at the sphere which is at rest initially, then you spin it up so that the rate of change omega dot is not equal to 0. So you spin it up so that it's accelerating, if you like, and then in its angular velocity or some time interval, and then let it come to rest. Now this changing, in this case, then we're going to changing magnetic dipole moment, and that sends out these electromagnetic waves up here. And then you can capture the photons that are emitted in the distant future. Now, if the detector, this is the important thing, just those who are not familiar with null infinity is an idealization. It just means that your detector is far away from the sources. Basically, if it is a distance r from the sources, which is very much larger than the wavelength of the light that is emitted, then you can use the null infinity approximation. Just as in your tabletop laboratory experiment, when you do scattering, you say that, well, something comes in from minus t equal to minus infinity, goes to t equal to minus plus infinity, etc. It's just happening in the lab, and that is just an idealization. The same thing is true here. Scri is just an idealization. So if I got an incoming state, then the angular momentum that is radiated away would be given by imaginary part of this part up here. Now, there is a nice bonus in this example. That's why I like this example very much. In this example, because of spherical symmetry of the source, it turns out that this quantity is identically 0. Oops. This quantity up here is identically 0. This angular derivative of a2 naught is identical equal to 0. And therefore, this quantity, yeah, just one second.
I'm confused. Why is it symmetric?
Say it again.
Just a confusion. Why do you say spherically symmetric is rotating? It's not spherically symmetric.
Yeah. So I'm sorry. So the charge is spherically symmetric. So it is true that the charge is spherically symmetric. It is true that it is rotating, and therefore it's the current is really only axis symmetric. It's not rotational symmetric. But this is because the sphere itself is spherically symmetric. I mean, it's something that you have to work it out, and I can show you the explicit expression for that a2 naught, and you'll see that the f of a2 naught is identically equal to 0 in that case. So f of a2 naught is equal to 0. It sort of if the source itself was not spherical symmetric, then this would not be true. So when I say source, I mean the sphere was not spherical symmetric, then this would not be true. But this is sphere which is rotating along the z-axis, then the statement is that this actually is 0. It's a calculation. And this actually vanishes. Okay. And therefore, the total angular momentum that is radiated away, so this line is here, J hat radiated away, is just given by this time this. Now, this is interesting because in the Fock sector, if these were the Fock photons, then this is identically zero. Therefore, there will be no angular momentum. They will carry no angular momentum in any up here, through any patch of sky up here. And the answer will be identically zero here for Fock photons. And therefore, you can do it as a null experiment, first of all. You can look at these photons and you can just measure if they carry angular momentum. Now, the classical theory says, yes, the classical waves carry angular momentum. So, I mean, the photons, so this angular momentum cannot just disappear. So the photons must carry angular momentum. So I'm completely convinced that you will find that the photons are carrying angular momentum, these photons. But these are not, but the angular momentum contained is completely non-zero, completely because of this Q of theta and phi. Because the photons carry Coulombic information, because photons are addressed with this Coulombic information, that the angular momentum is not equal to zero. I mean, the same thing was true in classical theory, but now we're talking about, this is important because of the photons had to have finite one particle norm. And that is why we got this non-Fock representation, etc. And the statement is that these new photons, if you like, are going to carry angular momentum. I strongly believe so. Otherwise, there is something wrong with the whole picture that I got up here. And then the statement is that, yeah, as soon as you see that they carry some angular momentum, you know that they are not the Fock photons. The second is that the experiment will also show that the Coulombic information is quantum mechanical. I mean, it's actually flux, this is quantum mechanical information. The photons are carrying away this angular momentum thanks to the Coulombic information that is encoded with them. And to reinforce that they are quantum mechanical, we could even measure both the expectation value of this angular momentum and its fluctuation and see that it is really genuinely quantum mechanical. And that is something that can be done. So the physical photons produced by such external currents cannot be described within the standard Fock representation. This class of photons these photons are distinct from those associated with the infrared sectors that are used in scattering experiments, because here the infrared charge is identically zero. And if the sources themselves are quantum field, okay, so that is what I want to say. And finally, I did not talk about this, but if sources themselves are quantum fields, then there are yet other effects. So these are various manifestations that the physical photons have many faces. Okay, so Mario says question, and perhaps there are also other questions up here. Maybe I should summarize and then take the questions. So summarize is basically, at first I did the standard Fock representation, quick summary, and I reformulated the standard Fock representation in terms of null infinity. There's nothing gained, nothing lost, but it's just a convenient representation. It just brings out the simplicity of the origin of the infrared sectors. Then I looked at the photons created by external sources. If the support is really a current of compact support in space-time, then we can live in the Fock space, again, assuming the source is such that we don't have infrared sectors. We can just live in the Fock space, carry out everything in the Fock space, and everything is as expected. That the outgoing, if the incoming state was vacuum, then outgoing state is a coherent state, peaked at the retarded solution. And if the current, however, is non-compact support in time, then the statement is that we really generically will get a non-Fock representation of photons if this Q of theta phi produced by the retarded solution is not equal to zero. And then radiated angular momentum in presence of sources, it is not fully captured by Fock photons, and you can have an experimental demonstration that physical photons carry Coulombic information. Okay, so there are several issues. This was Carlos' question, actually, which is, you can calculate what this A2 is, and in terms of the magnetic moment, and you can see up here that A2 is just given by that, and you can take its eighth, and you can check that the eighth of this A2 is identically zero. Then there was also a question of Mario's. So you tell me whether we should take Mario's question or whether we should have other questions here.
Okay, thanks, Abhay. Thank you for it. Everybody can join to thank Abhay for the presentation. We went quite a bit over time, but I made the editorial decision to let Abhay talk because I think this will be an excellent resource. And so, yes, I will open the floor to discussions. I guess you could start with Marius's question. Maybe Marius can unmute and ask it again, if just for context.
Thank you, first of all, Abhay, for the very nice presentation. Every time I listen to it, I think I understand a bit more. I'm not sure if it's an illusion or not. But so the question was about intuition. I've followed the calculations, but I still don't, how to say, I don't see what is physically happening, like intuitively, but maybe there is no good answer to that.
Yeah. So the question that Mario is asking is, why is it that the energy and linear momentum carried away by photons only cares about the radiative aspect, but the angular momentum also cares about the Coulombic aspect? That is Marius's question, right, Marius?
Yes.
Okay.
If you have an intuition of why this is the case.
Yeah. Right. So the thing is that we look at this stress energy tensor, and then we look at the flux associated with the Killing vector, any Killing vector field in Minkowski space through some region delta scri, and that will be integral of the stress energy tensor times Ca times the unit normal, which is just given by Na, and then I get here du and d2s. Okay. So now this du is some finite interval. So we could even look at the flux rate. Okay, we can look at the flux if you like. Okay. So now this F that we got, stress energy tensor that we got, that is just given by FAC, FCB plus is dual or minus a trace. Maybe that's easier. The two ways of writing it, so it's maybe easily result to minus trace. So that is the stress energy tensor with that. Now, this volume element, let's look at it in the physical space-time picture, because otherwise I have to do some calculation about conformal completion. So in the physical space-time picture, we can work in either picture. So in the physical space-time picture, we got this is a volume element which goes like r squared. Now, if I got a translation, this translation, if C is a translation, so TA, then its norm at infinity goes to 1 at infinity, or some constant at infinity, right? So it could be a unit time-like translation, unique space-like translation, etc. Its norm goes to 1. So therefore, this component up here is going to go to 1 at infinity. And A is just d by du, so its component at infinity is also 1. And what about TAB? So it better be that for energy, only that part will contribute up here where this falls like the component of TAB, which falls like 1 upon r squared. Because I got r squared here, and I got 1 upon r squared here, and therefore I'll get a non-trivial answer, right? If in fact that's what happens. Okay. So the flux of energy is going to be given by that part of the Maxwell field which contributes to stress energy tensor 1 upon r squared. But the stress energy tensor is quadratic in my Maxwell field, and therefore what I need is that. So in terms of FAB, I need FAB which is falling like 1 upon r, because I got here 1 upon r times 1 upon r, so that will give me 1 upon r squared. If I have, of course, I have components of FAB which fall like 1 upon r squared. But if I take 1 upon r squared component, so remember before that phi 2 naught goes like 1 upon r. Phi 2 goes like 1 upon r. Phi 2 naught is a 1 upon r component of it. So phi 2 goes like 1 upon r. Phi 1 goes as 1 upon r squared. So if in fact, if phi 1 were to contribute here, right, then phi 1 squared will be r to the 4th, and that would just, that contribution here, if I get r to the 4th, I'll just get 0. If I got phi 2 times phi 1, it will still be a 1 upon r cube, but the volume element is going only at r squared, and therefore that will not go to 0. So it is clear from here that the only part of FAB that contributes is the one which falls like 1 upon r, and 1 upon r is phi 2. And therefore, for the energy, I will find here that only that this is what is going to happen. Namely, for the flux of energy, I will find that only phi 2 will contribute. Is this point clear first? Marius, is this point clear?
So far, so good. Yes.
Okay, good. Okay. Now we look at angular momentum. So now we take C to be angular momentum, to be rotation. D by d phi. Now d by d phi is norm goes like r squared, right? Because CA, like phi A, if you like. D by d phi is just, its norm is going to be given by r squared sine squared theta. Therefore, the C goes like r. It doesn't go to constant. The time translation vector fields, where its norm is 1, they go to 1. But the rotation, d by d phi, is going to go like r. Okay? Here you go. So now we've got a new thing here. So if I look at now the angular momentum flux, but let me finish. Delta sky. I get here TAB times again C. C is now rotation. Maybe I should explicit write R just to make it clear. Rotation times NA times G2 S. Now this is going to go like R squared. This is going to go like 1 because this is a d by du is component is just equal to 1. And this is going to grow up. Therefore, what is going to contribute up here is the part which goes like 1 upon r cube. I mean, can contribute, can give you a non-zero answer that if this has part 1 upon r cube, because r and r squared. So terms of the order of 1 upon r cube will contribute. And now,
this is very silly
if you
question.
got phi 2 times phi 1, and that is exactly like 1 upon r cube. So here, phi 2 times phi 1 times that terms can come.
And why we don't get the divergence from the 1 over r squared?
That also happens at spatial infinity. You don't get divergence from what? From phi 2 times phi 2? No. What? Let me please ask the question.
No, I was saying, I mean, because now you have something that's going like r cubed in the, so this r and ds squared, and in TAB you will have 1 over r squared terms. So this integral could diverge.
No, but you're only looking at certain components, right? Here, I mean, we're not looking at all components. Well, look only. Here we're looking at, if you like, NN components or UU components. Here we're looking at we're looking at different components up here.
I see, thank you. So somehow it's because the angular momentum goes like R. You have more angular momentum when you're further away.
Yeah, I think Beatrice may be in the audience and she sends a message. So let's see here. Beatrice saying something.
Thanks, Abhay.
Yeah, Beatrice, okay. Yeah, okay.
Yeah, there was a discussion in the chat on whether the angular momentum included both orbital and spin.
Okay, thank you, Beatrice.
So if anybody has questions, they can raise the hand using the Zoom interface. In the meantime, I will actually ask a very naive question. Maybe you already mentioned it actually, but when we have the sources, the non-compact sources, and we were talking about how the two Fock spaces are not unitary equivalent. What is the way to see that there is no unitary map from one space to the other?
The usual way to do these things is always, I mean, there's also the same thing with the Bogoliubov transformation and so on. Maybe I should say a couple of things.
I'm sure, I know this is a standard procedure, but I've never fully internalized it. So in case.
So typical thing is that it's by contradiction. So you by contradiction, right? So you suppose that there is a mapping U exists such that in our case U times at of A to naught, whatever the operator you got here, so U is mapped into at of A to naught plus this what we had is Q theta phi. Q theta. Okay. Suppose there exists U, which does this for you on the Hilbert space, and then you say that it exists, and therefore you work out consequences. So in particular, typically what one does is to work out what is then U operating on the vacuum. That would be the simplest case to ask. Then it is very similar. You know, expand out this creation and annihilation operators and so on, and then you will get something. And then you will find that, I mean, the calculation of the type that I was doing before.
Get something with infinite norm or norm zero.
Yeah, we get something with, so we get a coherent state. Exactly. I mean, so you'll get a coherent state. So what is the image of this vacuum, right? And this is really the statement. The image of the vacuum in the future, in this U representation, if you like, is going to be this coherent state up here. So then here the same kind of mathematics, it's not the same problem, but same kind of mathematics will tell us, so what is this? So then the statement is that the same mathematics will tell you that U of O, this quantity is given by the coherent state. So it should be normalized times e to the minus, sorry, e to the, minus doesn't matter, e to the something times A dagger. It's a coherent state here. A dagger operate of U theta phi, sorry, omega theta phi times the thing that we had before. The d omega, not that. D omega times, in this case, as I was mentioning before, here I got here f of A2 plus omega. So here I had to first solve, I had to solve this equation. Basically, f of A2 is equal to Q. So that gave me that omega. So in this case, you will say that object which you call, sorry, this I should not, that one form omega, I'll put a different color up here. I got this one form omega, right? Which is such that dA omega A, two-dimensional dA omega A was equal to Q.
Right.
So that one form omega times I'll get here A dagger. Everything depends on omega theta. So, okay.
Right, yeah.
So you'll get that operating on vacuum. But then the question is this a coherent state? So is this one particle non-finite? This will be perfectly fine if the one particle norm is finite. But the point is that because this only depends on theta phi, this omega is in fact has a delta distribution. Singularity
because it's constant. Okay.
And therefore, in fact, it's one particle not yeah, it's because constant in U. Therefore, in the Fourier space, it will be yeah. So it's not normalizable. That's the main point.
Okay. Okay. So by contradiction, one I see.
Yeah, so there's contradiction. If you like, yeah, it's not normalizable. and therefore there's a contradiction. That's what, this is also the same thing that you do when you want to show in Bogoliubov transformation. There in quantum field theory in curved space-time or in external potential problems. So if I'm solving the potential problem, plus V of phi equal to 0, and if this V now can depend on X, and this is an external potential that can depend on time. Yeah, so if this depends on time, then again you want to know, so supposing you might ask, yeah. So in the distant past, you'll get one representation, Fock representation. In the distant future, you'll get another Fock representation, and you want to know if it is actually uniquely implemented. In this case, you get Bogoliubov transformations. For finite number of degrees of freedom, it always exists, but for infinite number of degrees of freedom, it doesn't always exist. And again, it doesn't always exist because in this case, you again assume there exists one, then the unitary transformation on this gives you a squeeze state. So e to the a dagger type of thing, operating on vacuum. And then with some coefficient up here, and then which this coefficient will depend on V. And then the statement is that you want to know if in fact this is a finite norm. And sometimes it does, and sometimes it doesn't. Typically, in quantum field theory in curved space-time, general time-dependent situations, typically it does not have finite norm, and then it is not unitarily implemented.
Okay, thank you very much, Sandra. There is a question by Ivan Agoya.
Yeah, please, Ivan.
Hi, Abhay. Thank you for the talk. Very interesting. I mean, it's very related to what you just said, so I think it's half already answered. But let me say it again. Anyway, I mean, from this viewpoint, it doesn't seem so surprising, right? That at the scrape class you need these these other kind of representations. Because we know what you just explained from quantum field theory in curved spacetimes, that a generic evolution produces a symplectic transformation, which is a type of squeezing, such that the norm of the final state is infinite in the initial Hilbert space. So here is similar. What you are saying essentially is that when you have external sources, these external sources produce a displacement of the state, right? So we know from quantum mechanics that the most general evolution is a symplectic, affine evolution, symplectic rotation plus a translation. And in curved spacetimes, we don't have the translation. You are saying that if you have external source, you have a translation, and if the source has some properties, that translation also kicks you out from the initial Fock space. But from that viewpoint, it's not so surprising or alarming, right?
No, it's not that surprising. And in fact, that was the thing that's why this first I had not looked at this particular problem, but I looked at the infrared problem in the 80s, and that's exactly what happens. Namely, in that case, if you got So in that case, the statement is that if you have some sources, I mean, but this was supposed to be the interacting case, right? I mean, like charge, like gravitating, like a Klein-Gordon field interacting with the gravitational field, for example, or charged Klein-Gordon field or something. Then the statement was that really, if you have sources, if you got a bunch of particles coming up here, then then in general, the mass, the analog of the q theta phi up here, let's say in this case, just q theta phi is not equal to 0. But if you have got sources which come in some way and go out in some way, then what they go out determines what is q theta phi here, if you like, the q plus theta phi. And here I get q minus theta phi. And the two are not the same. And that is what gives rise to the infrared problem. So I'd focused on that before, and it's exactly as you say, it's not surprising. I mean, you know this thing quite well, but the mathematical analysis is a little bit different in the case of in external current and external sources. In the case of external current, the space of solution is an affine space, And if you look at all of them, right, then the symplectic structure that you would not first write down would not be conserved classically. Because, for example, in this case, right, in this case, I can just have a zero field. So I can have a space-like surface here, and I can have zero field and a space-like surface here, and the field will not be zero. So I can have two fields whose symplectic, any two fields, their symplectic structure transformation here will be just zero, because I'm just taking zero field up here, but out here, I don't get zero field, right? So you have to be a little bit more careful about that. Namely, what you do is to make it a vector space artificially by introducing the retarded solution as the origin. And then it's a vector space, right? Because then the statement is that if the origin is not zero, but the origin is a retarded solution. So you have to do a little bit more work, but
right.
What you say is exactly right. It's not surprising. It is, I mean, conceptually, it's very, very similar.
It's not alarming, I wanted to say, it's, because we have seen similar things in other contexts, so it's not so exotic.
Yeah, no, that's not. It's exotic only from the point of view of, you know, the standard textbook treatment of photons in quantum optics books and so on and so forth.
Thank you.
From the point, yeah.
Yeah, I agree. A lot of this knowledge and techniques that have been seen by quantum field theorists in curved spacetimes are not necessarily common knowledge in other contexts, and it's really good to hear about it.
Okay. Can I ask one more question, Abhay? So for your, so you mentioned in the beginning mediated entanglement, and I think you hinted that this is somehow relevant or clarifying. Maybe you could say how you think about this.
Okay, so you're talking about
maybe it's, let me put the question more. So do you think this yes, do you think this clarifies something about the discussion on whether observing mediated entanglement would be witnessing something quantum about the gravitational field?
As I mentioned to you when I visited Vienna, although I don't agree with some of the technical things that are said in your paper with which I call CDHR, right? That paper. Conceptually, I agree with that paper quite, namely the Coulombic aspects are clearly quantum mechanical. This is one manifestation of that. The Coulombic geometry is completely quantum mechanical. There's nothing wrong with, I mean, and so with respect to entanglement thing, I mean, I've been discussing a lot with Eugenio and with Ivan, and we really don't understand the usual argument that is given in the standard papers, because in the standard papers, like for the BMV type of experiments, one makes use very much of the notion of locality, right? And the notion of locality they are using is system locality. So if I had, for example, quantum electrodynamics, then the system locality would mean that the unitary operator, that is evolution operator, will be unitary operator on the Maxwell space, tensor product to some unitary operator in the charged like Gordon field space. But we know what the Hamiltonian is in the perturbative treatment, and the Hamiltonian is just J dot A. If I take the unitary operator, then it is not of this form. So this idea what that is used in LOCC, that locality idea that is at the foundation of that whole discussion, is just violated in my view in the standard quantum theory, right? In the standard quantum electrodynamics. And since it's violated in standard quantum electrodynamics, I don't see how we can use it to conclude anything. On the other hand, I completely agree also with the thing that you guys had said in your paper, that quite apart from that argument, it is just true that the Coulombic field is really quantum mechanical. So I think that,
so trying to witness this.
I would like to say is that the standard.
Yeah.
Yeah. Okay. Carlo or somebody in Western has a question, I think.
Yeah, but actually, I think you have already said what what I wanted to ask you, and it referred to the last somehow the rival point in which you emphasize the quantum aspect of the Coulomb interaction. Once we view it in the context of quantum field theory, this comes because related to the, as you mentioned at the beginning, one motivation for some of the discussion relative to this issue came from the gravity entangled experiments. And of course, the gravity entangled experiments are in the non-relativistic limit. And in the non-relativistic limit, one can forget quantum field theory and says, okay, so I ignore quantum field theory. I just think in terms of non-relativistic theory. And in non-relativistic theory, I can imagine that Coulomb interaction is a long distance instantaneous interaction between which is fine. I mean, if one imagines the world could be non-relativistic, I could imagine that there is an instantaneous Coulomb interaction between the two quantum systems that get entangled, and this has nothing to do with radiative degrees with field degrees of freedom of gravity. But if the world is relativistic, we know that the world is not non-relativistic. The world is relativistic in the context of quantum field theory. The argument which has been put forward in the literature repeatedly that these experiments do not involve quantum aspects, in that case of gravity, because they only refer to the Newtonian interactions, they seem wrong to me, and it seems to me that the overall message of your beautiful general construction, and to the extent is related to that, is that no, I mean the Coulomb degrees of freedom are quantum like the others. They have to be treated, and they have a number of quantum properties. Of course, I think you would agree with that. This is if we bring to the interpretation of the experiment. The experiment is the non-relativistic limit, but if we bring to the interpretation of the experiment the knowledge that nature is not non-relativistic. So if we assume that it's a field theory, it is electromagnetism, in that in full quantum electromagnetism that describe the Coulomb interaction, then we cannot say that the Coulomb interaction is classical versus radiative photons being quantum.
I would say something slightly, I mean, as I said to Marius, I mean, we are the same. But the way, Carlos, I mean, one of the points that is not quite right in your paper is really this example in which, you say that I got a charge and then it accelerates, or it becomes time dependent and again becomes static later. And then, you point out a problem with the, not problem, but sort of counterintuitive thing. I think I understand, I agree with the spirit of the argument, but the particular example is not good because that particular example, the forecurrent is not conserved. And so therefore Maxwell's equations are violated. So in between arguments really cannot be applied in that particular example. This is just a side remark that I wanted to make to you because I've been wanting to write to you. But
if you think there's a mistake somewhere, just write to us and point it out.
I did tell Marius, so I thought that was enough that I told Marius, and right, exactly. So okay, but the point that you're just back, I mean, it's not a. I don't make any big, because I agree with the conceptual point that this decomposition is very non-local. I mean, if you give me the field in this room, I don't know what its transverse part is and what its longitudinal part is. It's very okay. But the main
technology of Scry, the syntactic technology, it's of course depending on the possibility of describing isolated systems, right? So it's the idea that a system is sufficiently isolated that you go at a distance, and once you're at a distance, you may make distinction between different components of the 1 over r, 1 over r square, and so on and so forth. So all this is not general, is not generic. It's only restricted to the case in which either the universe is asymptotically flat, or more specifically, we're describing systems sufficiently isolated for treating them in that language. That's what Roger Penrose always said, right, when he introduced this asymptotic methods. I mean, he said, of course, the universe might not be asymptotically flat. We don't think it is, but nevertheless, all these techniques are useful for describing isolated systems.
Yeah, I mean, it is not asymptotically flat, but I do laboratory experiments. I mean, every day, and I do scattering experiments, so non-relative quantum mechanics, and universe is not non-relative quantum mechanics, but I say that in the scattering experiments, I'm going to t equal to minus infinity, t equal to plus infinity, and the point is that, well, yeah, there are corrections, but good people have to check that those corrections are very small. So same thing here is true, right? But I think going to Scry for quantum electrodynamics or for gauge series is no worse, no better than working in Minkowski space. In fact, slightly better, but than working in Minkowski space, and everybody, all the analysis is done in Minkowski space. So, if you like, I take your analysis in Minkowski space and I just recast it in terms of Scry, and then the statement is that certain things become much more sort of stare at you, become obvious that were not obvious before. But if I had to go back to the main point that you were making, I made a digression. Yeah, so I think I agree that the Coulombic aspects are clearly, there's no question about it. And in the talk I gave in Vienna a few weeks ago, I even discussed this example of 2 plus. It is in the more recent preprint that I got on the archives. I discussed, for example, I said, okay, so there is all this confusion about Coulombic versus radiative degrees of freedom, and our Coulombic degrees of freedom, quantum, etc. So let's just go to 2 plus 1 gravity, where there is no radiative degrees of freedom. And is that really going to be? And just look at the example in which we actually quantize with matter. So there I consider quantum matter, which was supposed to be just a scalar field in 2 plus 1 dimensional system. And if it is axisymmetric, then you can actually solve this quantum mechanically exactly. And you see explicitly that there are quantum fluctuations. But the point is that those quantum operators, in that case, the geometry operator is completely an operator on the matter sector. It's a genuine operator. You can do experiments, like as you know, we can measure, the total mass, but in 2 plus 1 gravity, and total angular momentum by doing experiments of holonomy around using some test particles, right? We can just do that. And so, but the point is that the calculation, or conceptually, there's only one Hilbert space, which is the matter Hilbert space. There's no graviton Hilbert space at all. And yet, gravity operators are operators on the matter Hilbert space, and they have completely quantum mechanical properties. And so this last part that I just mentioned, but I did not at all talk about it really. It is really, it's really has to do with the fourth part, basically, is going beyond what we're doing now and talking about perhaps sources are not classical sources, but sources are quantum mechanical sources. So for example, you have got charged Klein-Gordon field or charged Dirac field coupled with electromagnetic field. And we can have a top-down approach, and we just start with quantum electrodynamics and then make successive approximations to come to what is the usual non-relativistic limit. I have not found any good treatment of this. I asked Vienna people, they also did not find. Things like Cohen-Thanujian book and so on don't really do it. They just state the result, basically. But Eugenio and I have been talking a lot about this, and I think that really is something that is possible coming from that. But again, what one would find is that the Coulombic aspect of the electromagnetic field, in that case, is genuinely quantum mechanical. But in that case, since the source is quantum mechanical, there is also source Hilbert space. In the external potential, in the external current problem I talked about, the source is classical. So there is no Hilbert space for source. So in that case, I got a Hilbert space for sources and Hilbert space for photons. And the Coulombic aspects are really operators, which are non-local operators, but still operators on the source Hilbert space. But they are quantum mechanical properties. There's no problem. So I'm completely agreeing with you, but I'm providing a slightly sharper version, namely, where do those operators live? And those operators actually live on the source Hilbert space. I'm being very rough here, but that is the general idea. So that will be the next step, because in this state, the source is classical, so there's no source Hilbert space. So I only have if like the Coulomb things just get shifted. But now the shift is related to the classical source, right? This Q of theta phi was related to the classical behavior of the classical source. If in fact everything is quantum mechanical, then the things are related to really the Hilbert space of matter. So this Q of theta phi here was just a C number. In that case, Q of theta phi is living on the Hilbert space of the matter. It's much more complicated construction, but I think it's a bit like what happens with infrared sectors, but this is another aspect of non-standard Fock representations. Are you happy, Carlo, with what I'm saying, or do you have any suggestions, comments?
Yes, completely. Yes, and especially the fact that if the matter is quantum mechanical, an operator that depends on the field, which in terms depend on the matter, is quantum mechanical as well, of course. And in gravity, if we think in a simplified setting in which there are particles interacting with the gravitational field, because of diffeomorphism invariance, it's hard to separate the Hilbert space of the particle from the Hilbert space of the metric, so to say. So the relevant operator here is the distance between the two particles, but the position of the two particles on the one hand and the metric field in between are not diffeomorphism invariant. So the only thing one has is the as a diffeomorphism invariant quantity is a distance. So the separation between a matter Hilbert space and a gravitational Hilbert space is very much blurred in gravity. So in gravity, it's even more hard to separate the two things. So it's even more obvious that the distance, which is the relevant thing in that case, it's a quantum object in a quantum theory, which sort of depend on both.
But that is why one has to sort of resort to perturbation theory, and that's what people with the infrared sectors do, right? I mean, they have these incoming particles from I0 because they're massive particles, so they're sources. They think of them as really quantum fields, like Planck-Gordon field or something like that, or massive particles coming in and gravitational scattering, but it's usually used in the scattering context. And what we want to do is to use these methods in the lab experiment context, where I mean, you can use chi plus, chi minus, but we shouldn't emphasize too much about scattering amplitudes. What we are interested in is really interaction between particles at a finite distance. I mean, and that is where what Carlos says is exactly these difficulties come into limelight. Good. Are there any other questions, comments, or should we quit soon?
There are no further hands raised, and you are very generous with your time, so I think we can wrap up. Thank you again. Please join me in thanking Abhay again for the presentation, the discussion, and everything. And see you all for the next his seminar, which will be by Markus Müller, I think in March. Thank you.
So thank you.